As the 20th century gave way to the 21st, the pace of technological change accelerated like never before. Innovation became global, digital, and constant, reshaping not just how we live, but how we think, communicate, and interact with the world. Although the internet was born in the 1960s as a US military project, ARPANET, it wasn't until the 1990s that it became a household phenomenon. Thanks to development of the World Wide Web in 1989, the internet evolved from a network for researchers into an open system of hyperlinked pages accessible by anyone. By the early 2000s, the internet had transformed communication, commerce, and knowledge. It connected people across continents, democratized access to information, and began reshaping economies. In 2007, smartphone marked a turning point. No longer was the internet something accessed through a desktop, now it lived in your phone. The smartphone combined a phone, camera, web browser, GPS, and media player into one compact device. With the rise of apps, smartphones became tools for navigation, communication, media, productivity. Artificial intelligence, once limited to academic theory, began maturing rapidly in the 2010s, thanks to vast datasets and increases in computing power, especially with GPUs. Machine learning and deep learning became viable. AI now powers recommendation systems, language models, and chatbots, medical diagnostics, autonomous vehicles, financial forecasting. These aren't just programs, they are adaptive systems that learn from data and can improve over time, opening new possibilities and also raising ethical questions about bias, privacy, and control. In the modern world, automation means more than assembly lines and conveyor belts. It refers to machines, physical or digital, that can perform tasks without constant human intervention. Automation today is powered by a blend of technologies, sensors and robotics, artificial intelligence, cloud computing, and Internet of Things. From automated warehouses that restock and sort inventory with barely any human hands involved, to AI algorithms that detect fraud in banking or recommend treatments in hospitals. Automation is being deeply integrated into every sector. The result: higher efficiency, fewer errors, but also rising concerns over job displacement, surveillance, and algorithmic bias. But as the digital revolution intensified, a fundamental question began to surface. Since the 1960s, the power of classical computers has been governed by Moore's law. The observation that the number of transistors on a microchip doubles roughly every 2 years, making computers faster and smaller. For decades, this prediction held true. Transistors, the on and off switches of computing, shrank from the size of a fingernail to nanometers across. But as we approach atomic scales, we run into the boundaries of quantum physics. As extremely small scales, Heisenberg's uncertainty principle becomes significant. This principle states that we cannot know both the position and the momentum of a particle with absolute certainty. When transistors are only a few atoms wide, electrons no longer behave predictably. They tunnel through barriers, making binary logic unreliable. This isn't just a technical challenge, it's a fundamental physical limit. We can't shrink classical computing forever, so instead of fighting quantum behavior, scientists decide to harness it. Unlike classical computers, which use bits, zeros, or ones, quantum computers use qubits. A qubit can exist in a state of 0, 1, or both at once, a phenomenon called superposition. Additionally, qubits can become entangled, meaning the state of one qubit instantly affects the state of another, no matter how far apart they are. This property enables complex computations to be distributed in ways that classical systems cannot replicate. This potential makes quantum computers especially powerful for factorization of large numbers, molecular modeling for pharmaceuticals, optimization problems in logistics and finance, weather and climate simulations. Quantum computing is still in its infancy. Qubits are delicate, they suffer from decoherence, losing their quantum state due to tiny vibrations or temperature changes. Maintaining stable quantum states requires near absolute zero temperatures, extreme isolation, and error correction. Companies like IBM, Google are building early machines with tens or hundreds of qubits aiming for quantum advantage, the point where quantum computers outperform classical ones at useful tasks. Quantum computing represents more than faster machines. It is a paradigm shift. Where classical computers rely on certainty and binary logic, quantum computing embraces probability, uncertainty, and parallelism. It doesn't just solve harder problems, it redefines what kinds of problems we can solve.